Good afternoon, ladies and gentlemen. Welcome back to Flawless 195. I'm Captain Wilson, and this is flight 99 of 210. It's Gaborone to Windhoek in countries Botswana to Namibia. If you are new to the channel, please do watch the route explainer video before you go any further. If you have to scroll back, I think it's after about 25 flights, I post the route explainer. And if you are a returning viewer, then please do get yourself subscribed. Departure time from Gaborone is going to be 1:30 p.m. local time for a total flight time of 1 hour and 10 minutes over to Windhoek, the capital of Namibia. We'll be heading west, slightly northwest actually, before then heading south. Directly south to the southernmost tip of South Africa for flight 100 to Cape Town. Interestingly, South Africa has, I think, 3 recognised capitals. I've gone for the southernmost one just to, I don't know, feels right. Furthest one away. But anyway, that's flight 100. This is flight 99, Botswana to Namibia. 1 hour and 10 minutes heading west. Yeah, let's get on with it. We're heading for Eros Airport, Windhoek. We haven't got ILS in, so I'll have to make a deviation south before we'll be landing northbound. So I'll have to sort of dip south and then swing it round up to the north, and in we go. We've got vehicles queuing up here. I need to get out of here. But where are they going? What are you going to do? Oh, brilliant. Oh, brilliant, isn't it? They don't know where they're going and they don't know what they're doing. Right. Anyway, we've got enough vehicles dipping around. We'll try not hit any. But yeah, let's get on with it. I'll get the safety demo on, and then once we're in the air, or well, after the safety demo, I'll get the Lemino documentary on for the final part. Because there is about 40 odd minutes left of this flight, is over an hour, so we'll get through that. And yeah, so we'll finish the space documentary that we've had for the last couple of flights. But yeah, welcome to flight 99 of 210. The world tour continues, ladies and gentlemen. Gaborone to Windhoek, here we go. Right, I'll speak to you when I feel like it. See you in a bit.
Please pay attention to illuminated signs and crew instructions, including the following safety procedures. The safety card found in your seat pocket contains important information about exit routes, oxygen masks, life jackets, and the brace position that you must adopt if you hear brace, brace. There are 8 emergency exits on this aircraft. The cabin crew are now pointing out the exits nearest to you. Please be aware that your nearest usable exit may be behind you. Emergency lighting will guide you to an exit. In an emergency, leave all baggage on board. Your seatbelt is fastened, adjusted, and released as shown. It must be fastened when the seatbelt signs are on, and we recommend that you keep it fastened at all times. If the air supply fails, masks will drop from above you. Pull a mask towards you to start the oxygen. Put the mask over your nose and mouth and breathe normally. Hold the mask in place with the strap. Pull on each side to adjust. Put on your own mask before helping others. If we land on water, take a life jacket from under your seat. Remove from the pouch and put it over your head. Pass the tapes around your waist and click together. Pull the strap to adjust. Do not inflate it inside the aircraft. When outside, inflate it by pulling the toggle. If it fails to inflate or needs topping up, blow into this tube. There is a light and whistle for attracting attention. The cabin crew can assist you with life jackets for children. Your tray table must now be stowed, armrests down, window blinds open, and seatbelt fastened. Further information regarding your safety on board can be found in the in-flight magazine. We hope you have a great flight.
To commemorate the 400th anniversary of astronomical contributions made by Galileo Galilei and Johannes Kepler in 1609, the United Nations, along with the International Astronomical Union, declared 2009 the International Year of Astronomy. Unsure of how best to celebrate this milestone, a representative of the Australian government reached out to a popular science magazine known as Cosmos. The magazine's editor-in-chief, Wilson da Silva, suggested they transmit an interstellar message during an upcoming annual event known as National Science Week. They were soon given the green light by the government, and after consulting a bunch of astronomers, NASA and others, Cosmos launched a website called Hello from Earth. The project was described by da Silva as Twitter to the stars because the idea was to allow anyone to submit a brief text message of no more than 160 characters in length. When the submission period came to a close less than 2 weeks later, the website had received nearly 26,000 messages. According to da Silva, less than 1% of the comments contained some sort of rule-breaking content like profanity, slurs, and so on. They were also forced by NASA to remove anything deemed even remotely sexual or aggressive, like the word breast, and the phrase, "all your bays are belong to us," which is just a line from an old video game that later became a meme. As someone who's old enough to have been around back when this meme was still popular, this might be one of the most depressing things I've ever had to explain in a video. Painful reminders that we're all stuck in a travelator towards eternal nothingness aside, once all the messages had been vetted and approved, they were transmitted from a large antenna at the Canberra Deep Space Communications Complex in the Australian southeast on August 28, 2009.
Hello from Australia, on the planet we call Earth. These messages express our people's dreams for the future. We want to share those dreams with you.
To be or not to be? That is the question.
I'd like to invite you all back to my place for a few beers.
Klaatu, Barada, Nikto.
Does the meaning of life equal 42? If not, please explain.
Please come and save us from ourselves.
Do you plan to invade?
Which way does the water spin when you flush the toilet?
How is it that you understand English? That's very convenient.
Hey guys, great to catch up the other day. We'll discuss intergalactic trade policy next week. Keep it on the hush-hush, remember?
We're no strangers to love. You know the rules, and so do I. A full commitment's what I'm thinking of. Never gonna give you up, never gonna let you down.
We are destroying our planet and are too selfish to stop. We need your help. Please, come quickly.
We're mostly harmless.
Do you have any updog on your planet?
Apologies in advance for most of these messages. They are an example of our primitive humour.
Live long and prosper.
Hello from planet Earth.
Much like a message from Earth, Hello from Earth was also directed towards the nearby red dwarf Gliese 581. As mentioned before, observations conducted back then suggested the presence of 2 planets within the star's habitable zone, but those findings have since been refuted. Nevertheless, Gliese 581 is now the second star to be signaled more than once, after 47 Ursae Majoris. While the International Year of Astronomy was primarily dedicated to Galileo and Kepler, 2009 also marked the 35th anniversary of the Arecibo message, something that American artist Joe Davis decided to celebrate in his own unique way. One of the most vital biological mechanisms on Earth is photosynthesis, the ability of some organisms like plants and algae to produce life-essential oxygen using water, sunlight, and carbon dioxide. Now, a crucial component of photosynthesis is a special molecule known as rubisco. Rubisco is what's known as a protein,
Cabin crew seats for takeoff.
enzyme that's been around for billions of years. Presuming the evolution of life here on Earth is typical rather than special, one possible way to communicate with an alien species would be to send them very basic biological information. If their path to intelligence bears any resemblance to our own, there's a chance they'll recognize an enzyme as ancient and rudimentary as rubisco. This was the idea that occurred to Joe Davis in late 2009, But instead of using something more conventional like binary code, he decided to map the Rubisco gene sequence to 4 increasingly syllabic phrases alluding to an ancient Greek proverb. These were then vocalized and turned into a 15-minute audio sample using the text-to-speech feature on a regular iPhone. Now, if you feel like you couldn't quite follow all of that, no need to worry, there's zero chance the aliens will either. Much like Davis's previous project, the Rubisco Stars message was largely symbolic and primarily intended to evoke a reaction from people here on Earth. Nevertheless, using his academic connections, Davis managed to book time at the Arecibo telescope. Then, on November 7th, 2009, just over a week before the 35th anniversary of the Arecibo message, a frequency-shifted audio recording of a synthetic voice rattling off fragmentary sentences representing the Rubisco gene sequence was beamed towards 3 nearby stars.
Know yourself, the riddle of life, the I know yourself, I know yourself, I know yourself, know yourself, know yourself, I know yourself, riddle of life, know yourself, riddle of life, know yourself, I am the know yourself, know yourself, know yourself, riddle of life, I know yourself, know yourself.
The first target was T-Sed Arietis, a red dwarf less than 15 light-years away with 1 confirmed planet approaching the mass of Saturn. It's a very active flare star, so even if an Earth-like planet could be found, it's unlikely to host life as we know it. Meanwhile, the third target was Kappa 1 Ceti, a Sun-like star barely 30 light-years from Earth. While it is similar to the Sun, it's also a lot younger, making it unlikely that sufficient time has elapsed for a communicative civilization to have emerged. But the second target is a lot more interesting. It's another red dwarf known as Teegarden star, and while it does exhibit occasional flaring, it's a lot older and much less active than most of its kind. Furthermore, it's home to 3 confirmed planets with masses very similar to that of Earth, and 2 of them orbit within the habitable zone. To quote a recent paper, they are among the most Earth-like exoplanets currently known. But Earth-like does not necessarily mean habitable, because flares are but one obstacle that red dwarf planets have to overcome. Another potential hazard is something known as tidal locking. Without going into too much detail, the simplest form of tidal locking is when the rotation of a celestial body becomes synchronized with its orbital period. The most famous example of this is the Moon. It completes precisely 1 rotation for every orbit around the Earth, which is why we only ever see one side of the Moon. The reason this happens is a bit complicated, but it's tied to proximity. The tighter the orbit, the more likely it is for a celestial body to become tidally locked to its host. As you can imagine, planets orbiting red dwarfs are especially susceptible, as they have to orbit very close to their star to retain liquid water on their surface. Sure enough, the 3 planets orbiting Teegarden star are all believed to be tidally locked, just like the Moon. This is less than ideal because it means that one hemisphere is cooked by everlasting starlight while the other is plunged into eternal night. Habitability estimates for such bisected worlds range from extremely pessimistic to cautiously optimistic, because some climate models suggest warm air from the day side creeps into the night side, which pushes cold air from the night side into the day side, and so on. The end result of which is a planet with a surprisingly temperate climate that keeps water at perfect equilibrium between freezing and evaporating. But even if we accept the more optimistic models, the proximity of red dwarf planets also makes them less likely to retain an atmosphere in the first place. That's because stars tend to shed vast quantities of material into space, and the closer you get, the more intense that stellar wind becomes. As if that was not bad enough, this wind is occasionally interrupted by more explosive events like coronal mass ejections that can expel billions of tons of superheated plasma in a matter of minutes. Here's one being ejected from the Sun, with the Earth hauntingly to scale. In the case of Teegarden star, the 2 innermost planets are between 9 and 15 times closer than Mercury is to the Sun. It only takes them 11 and 5 days respectively to complete an orbit. According to one recent study, that's close enough for the stellar winds alone to completely strip those planets of a lasting atmosphere. While atmospheric erosion could be mitigated by a strong magnetic field like the one that surrounds the Earth, The magnetosphere of tidally locked planets would likely be reduced by their sluggish rotation. All that being said, the habitability of red dwarf planets remain open to debate. There is so much we don't know, and theories, simulations, and mathematical models can only do so much to fill in the blanks. Red dwarfs account for approximately 3/4 of all stars in the Milky Way, so it would be a real shame if not a single one of them can support life as we know it. It's possible that some environments are conducive to life, while others are not. The tricky part is determining where that line should be drawn. Presuming the planets orbiting Teegarden star have in fact cradled beings of sufficient intelligence, a reply to the Rubisco star's message could be heading our way right this very moment. The signal would have reached the Teegardenese back in 2022, which amounts to a round-trip ETA of 2034. Don't forget to mark your calendars. No, genuinely this time. Late one evening on August 15th, 1977, the Big Ear Telescope in the US state of Ohio performed a routine survey of the sky. A few days later, a volunteer named Jerry Eman sat down to review the collected data. What he found was a signal so exceptionally strong that he encircled the sequence on the printout sheet and famously wrote "WOW" in the left-hand margin. The WOW signal remains a mystery to this day, not least of all because it was never detected again despite numerous attempts to do so. The sequence 6EQUJ5 is not some sort of code but merely the intensity of the signal over time, where numbers above 9 are represented by letters to save space. It makes a lot more sense if we plot it onto a graph like this. It begins with a value of 6, meaning it was 6 times more intense than normal background noise. The signal then jumped up to 14, followed by 26, and a peak intensity of 30 times above background. The signal then fell back to 19, and then 5, before it disappeared. Each of the 6 samples were recorded 12 seconds apart, and this 72-second rise and fall is perfectly consistent with the telescope panning over the source along with the Earth's rotation. In other words, the source of the WOW signal appears to have been more or less fixed in the night sky, much like a distant star. Had it been an Earthbound source, it would have moved with the telescope, while things like airplanes and satellites would likely have moved too fast to remain visible for the whole 72 seconds. The WOW signal was also tantalizingly close to the frequency of the aforementioned hydrogen line. This makes it even less likely to be man-made because it falls within a protected band of frequencies reserved for radio astronomy. On top of that, it had a very narrow bandwidth. What this means is that unlike a star, for instance, which emits radiation across a wide spectrum of frequencies, the WOW signal was very focused. It's by no means impossible for a natural source to produce such a concentrated beam, but it is unusual. This is what makes the WOW signal so curious. It bears all the hallmarks of a technosignature. Just as we have identified hydrogen, the most abundant element in the universe, as a means of initiating contact, the aliens could have done the same. Just as we tend to transmit extremely brief, non-repeating messages, the aliens could be doing the same. Unfortunately, the peculiar design of the Big Ear Telescope makes it impossible to pinpoint the source of the signal. The setup was such that 2 large swaths of sky were scanned simultaneously, but there's no way to tell them apart when looking at the data. Even more peculiar is that the signal was only detected once despite this dual scanning design. This can only mean one of 2 things. Scenario 1 is that the source had been transmitting for some indeterminate amount of time ahead of the first scan, yet ceased transmitting before it could be detected again by the second. Scenario 2 is that the source began transmitting during the roughly 3-minute window between the 2 scans and continued to do so for who knows how long. Now, for a signal to carry information, it has to exhibit some sort of pattern. For instance, we tend to encode our messages by encoding a binary pattern that shifts back and forth between 2 different frequencies or levels of amplitude. The WOW signal did not exhibit any such pattern. Both its frequency and amplitude had a constant, unmodulated appearance throughout the whole thing. That being said, we can't rule out the possibility that a sequence of fluctuations were present, but that they fell below the threshold of what the Big Ear Telescope could detect. No instrument has infinite resolution, and Big Ear had some quite significant blind spots. To quote Eman,
"Any variation of signal amplitude within the 12-second interval would not have been detected.
The signal could have been varying in any of a variety of ways, and we would not have seen it.
On the off chance that the WOW signal was a message from another civilization, the National Geographic Channel decided to transmit a reply on its 35th anniversary. After collecting over 17,000 tweets and about a dozen video-recorded greetings by various celebrities and public figures, the WOW reply was beamed into space from the Arecibo telescope on August 15, 2012. At least, that is what the public was told. But after contacting someone who worked at Arecibo when this transmission took place, they told me that the stress of beaming thousands of messages into space had caused the aging transmitter to overheat and break down. They could not recall how many messages made it through, but it could have been as few as just a single one. Now, because the details of the project had already been publicized ahead of time and no correction was ever issued, everyone assumed that the WOW reply went off without a hitch. But not only is it unclear how many tweets were sent, it's also unclear where they went, because the WOW reply had 3 intended targets. They were all sun-like stars known as HD 54351, 37 Geminorum, and 55 Cancri A. Very little is known about the first, and it's quite some distance away at 140 light-years. Meanwhile, the other 2 are much closer and have both been targeted by previous METI experiments. The person I spoke to could not recall which one was targeted first, so my best guess is HD 54351 because that's the one listed first in a press release about the project. Now, with a name like WOW reply, you'd think the 3 targets were located within one of the 2 regions from which the WOW signal is known to have originated. Well, if you did think that, it might be time to recalibrate your common sense, because all 3 targets are not only located outside of these regions, but in the complete opposite direction. The reason for this is very simple. The location where the WOW signal was detected was beyond the reach of the upward-facing and stationary Arecibo telescope. But if that's the case, why even call it the WOW reply in the first place? Apart from being transmitted on its 35th anniversary, none of this had anything to do with the WOW signal. While the signal does have the hallmarks of an alien transmission, there's still a very good chance it was caused by natural phenomenon. It's just a matter of identifying the correct one. For instance, one recent hypothesis tried to blame the whole episode on a pair of passing comets, but like all previous explanations, this one has failed to withstand further scrutiny. More recently, a paper published in 2024 hypothesized that a powerful flare ejected by something like a magnetar could have been amplified by a cloud of hydrogen, which would explain the signal's frequency. Whether this is the solution that will finally crack the case or be relegated to the mounting list of dead ends, only time will tell. In the early 2010s, a film editor named Pierre Fabre conceived of a project dubbed Lone Signal. Much like Team Encounter and the Cosmic Calls, Lone Signal was an attempt to commercialize interstellar messaging. The project was envisioned as a social media platform where anyone could submit text, images, audio, and video for direct transmission into space. Another similarity between Lone Signal and the Cosmic Calls was the inclusion of a primer written in a mathematical language of sorts. Constructed by planetary scientist Michael Bush, every component of this language is represented by a string of 8 digits between 0 and 7. For instance, 1 + 1 = 2 looks like this, and here on the right is an example of some basic algebra. Things only become more complicated from there, but I'll spare you the details because according to Bush, the technique used to encode the primer into the signal was far too fragile to survive the years-long trip across interstellar space. While the signal could still be detected, any patterns would become scrambled along the way, making it impossible to extract and decode the primer at the destination. In other words, alien astronomers may end up with their own WOW signal that doesn't seem to fluctuate in any meaningful way, yet whose properties may still be difficult to ascribe to a natural source. Now, what truly sets Lone Signal apart from every other initiative mentioned so far is that it wasn't a one-time thing. Instead of transmitting the primer and public greetings all in one go, Lone Signal sought to establish a permanent beacon that would continuously transmit for years or even decades. To make that happen, they couldn't just book time at an active observatory, but had to obtain long-term exclusive control over a telescope. After shopping around for a bit, they eventually secured a 30-year lease on a decommissioned telescope in southwestern California called the Jamesburg Earth Station. Then, after upgrading some of its aging equipment, Lone Signal began transmitting on June 17, 2013. But the team behind Lone Signal had even greater ambitions. Their long-term plan was to raise $100 million and to establish a network of telescopes to continuously signal multiple targets all at once. They likened themselves to SpaceX and hoped to create a global platform from which anyone in the world could beam any random thought directly into space all day long. But in a classic case of history repeating itself, the team behind Lone Signal, much like Team Encounter before them, vastly overestimated the public's interest in METI. Less than 2 months after launch, revenue from the website barely covered 2% of their operational costs. Pierre Fabre later wrote in a comment, "We failed to connect with our audience on a colossal scale, and that failure led investors to ultimately pull the plug." Nevertheless, the transmission target was yet another red dwarf called Gliese 526. It's less than 18 light-years away and about twice as old as the Sun. While it is a relatively quiescent star with only occasional flaring, a planetary system has yet to be detected. Should it be home to a spacefaring civilization, they will have upwards of 2 months to notice
Again,
our
a
cosmic
waste of
counting,
time.
beginning
Again,
early
I said this
2021.
yesterday. Why are they sending these signals to places that don't even have planets? There's only been one example out of all those examples. There's only been one example of a place that's worthwhile sending a signal to. Out of the, I don't know how many examples he's gone through, maybe 10, 12 different signals that were sent over the years since the 60s or whatever. Out of the 10 or 12 different signals or messages that we've sent, I think there's only one, and it was as I was getting ready to take off, I nearly come on the microphone and said, "Oh, that one makes sense." I think there's one, just as I was getting ready to take off it for this flight here, where he actually said, right, there's potential, there's 3 planets here, and similar to Earth. And I thought, oh, about fucking time. So out of all these messages and signals that they've sent, say there's been 12, 11 out of 12 of them absolutely pointless. Absolutely ridiculous. I don't know who's picking out where they're being sent. I said this yesterday anyway, I'm repeating myself. But I don't know who's picking out where these signals have been sent. But it's so bad, it's like sabotage. Anyway, carry on. We'll never get through this documentary, will I? Keep rabbiting on. Anyway, let's
Back
carry on.
in prehistoric times, not long after you pressed play on this documentary, I mentioned a series of METI experiments carried out by the National Space Development Agency of Japan in the mid to late 1990s. Designed by young students attending a NASA space camp, these 5 bitmap images were transmitted from the Yasuda Deep Space Center to various locations across the galaxy. Fast forward to 2013, and the successor to NASA, the Japan Aerospace Exploration Agency, decided it was time to try again. During a similar space camp event and using the same telescope as before, JAXA retransmitted this image of 2 parents and a child on September 22nd, 2013. A similar bitmap depicting a human standing next to the sun was then transmitted the following year on August 23rd, although it's unclear exactly what it looked like. Nevertheless, both images were directed at 55 Cancri A, which has been targeted in the past and discussed in more detail in a previous chapter. But much like what happened back in the 90s, the JAXA Space Camp messages flew as much through the radar as they did under it. Instead, these events were largely overshadowed by new developments in the ongoing transmission debate. Most notably, in early 2015, over 24 scientists and SETI enthusiasts, including a pre-disgraced Elon Musk, signed a petition calling for a worldwide consensus regarding METI. They took issue with the fact that past METI experiments had been based upon the wishes of a few individuals rather than a broadly representative body, in part because the aliens are likely to be millions of years more advanced than us, but also because it is impossible to predict whether they will be benign or hostile. The petition concluded that the potential consequences of contact demanded worldwide scientific, political, and humanitarian discussion in advance of any future transmissions. to which an artist in collaboration with the European Space Agency responded,
Anyway, I started blasting. Bah, bah, bah.
In early 2016, an artist and independent researcher named Paul Quast created a crowdsourced art project known as A Simple Response to an Elemental Message. It was similar to previous initiatives, except this time people were asked to frame their submissions as an answer to the question, how will our present environmental interactions shape the future? As the question implies, the project was about climate change and sought to capture a global portrait of humanity's thoughts and feelings about the present and future state of the world. As explained by Quast in a few interviews, the project was intended more as a time capsule for future generations than any potential aliens in outer space. This is also reflected by the selection of Polaris as the transmission target. As mentioned in a previous chapter, it's a relatively young and currently planetless system that's highly unlikely to host life as we know it. Instead, Polaris was primarily selected due to its historical significance as the famous North Star. Nevertheless, A Simple Response to an Elemental Message received nearly 4,000 submissions over the course of about 8 months. In addition to the public messages, Quast also included a few copies of the Arecibo message, 81 quotes by prominent figures, and 70 photographs of Earth and humanity, all of which was then converted into binary and finally blasted into space by the Cebreros Deep Space Ground Station in central Spain on October 10th, 2016.
Our present environmental interactions are going to have us searching for a new home. So if there are any aliens out there renting out any space apartments, we'll be looking for 2 bedrooms, 2 bathrooms, and maybe a nice view of your 2 suns.
We have proven that a single species is chemically capable of altering the biosphere. Now we must prove that one is capable of amending it.
I think that if we were to challenge our ways now, it is unfortunately too late to remedy a solution for the future. The damage is done.
All of this concern for the future hinders optimism for what we have already achieved to secure it. We have progressively steered our civilization away from many existing threats.
The turning point of our time will be when our species achieves nuclear fusion to push us out of the era of carbon fuels and into a more sustainable society.
I am optimistic, and I am sure that humanity will be able to coexist with nature and in peace.
Our present interactions with the ecosystem will destroy human life long before Polaris gets this message.
According to a subsequent review by Quast, he found that just under 20% of the respondents were optimistic, just over 42% expressed some form of dread or concern, while the remaining 38% were largely neutral. In late 2017, a Spanish music festival known as Sonar began transmitting brief snippets of music into space to commemorate its 25th anniversary. Each composition was no more than 10 seconds in length and were provided by 38 musicians with connections to the festival. The first 18 were transmitted over the course of 3 days in October 2017 from a telescope located in the far north of Norway. The remaining batch of 20 was then transmitted over the course of another 3 days in May 2018 using the same facility.
In the intro, it says music from all over the world. Hey, I can up the ante on that. Music from all over space.
In fact, not just
Come
one,
on.
but several.
Flawless
The first one
195.
began with 2 lists of prime numbers intended to attract
Hey,
attention.
begs
while
the
the primes
question.
were technically expressed in
All this begs the question, what did I do once I've done the world tour? Space. Every planet. Come on. Got to up the ante, don't I?
binary, it would be more accurate to say that they're expressed in unary repeated twice. So 0011 for decimal 2, 000111 for decimal 3, 00001111 for decimal 5, and so on. This was followed by a simple count from 0 to 255, expressed using 8-digit chunks of binary code, also known as a byte. So it goes from 8 zeros representing 0, all the way up to 8 ones representing 255, the highest value possible using 8-bit encoding. Okay, following that introductory sequence was a second primer that differed between the two sessions. The one included with the first batch of music was written such that all 256 bytes represented a unique number, word, or concept. These bytes were then used to convey increasingly complex ideas, much the same way it's been done in previous initiatives, starting with some basic math before delving into things like physics and sound. The one included with the second batch of music was nearly identical to the one created by Ivan de Til and Stéphane Demas for Cosmic Hall 2. Some of the components have been shuffled around and there's some updated information about the telescope, but otherwise it's exactly the same. Immediately following that was another bitmap that tried to graphically convey the concept of a byte by counting from 0 to 255 once again. This was then followed by an image of a sine wave intended to visually convey the concept of sound and music. Now, the target of these transmissions was an ancient red dwarf known as Luyten's star. It's a bit more than 12 light-years away and harbors 2 confirmed planets, the outermost of which, Luyten b, is about 3 times the mass of Earth and orbits within the star's habitable zone. In fact, it is one of the nearest Earth-like planets ever discovered, and it's the sole reason that this system was targeted. But as mentioned previously, the characteristic dimness of red dwarfs places the habitable zone very close to the star. In the case of Luyten b, it orbits about 4 times closer than Mercury orbits the Sun, takes less than 19 days to complete the revolution, and is all but guaranteed to be tidally locked. On the plus side, Luyten's star exhibits minimal flaring due to its advanced age. Presuming Luyten b is inhabited by an advanced civilization, they'd have about 11 minutes per day for 3 consecutive days in early 2030 to pick up the first batch of music, with the second arriving a few months later. Presuming they do so, we could hear back from the Luytenians as early as 2042. Okay, we have finally reached the most recent interstellar message as of the making of this documentary. Well, kind of. We'll get to that in a moment. Following the death of Stephen Hawking in early 2018, his ashes were interred at a famous church in London called Westminster Abbey. As the memorial service came to a close, an original score set against Hawking's iconic voice and written by Greek composer Vangelis was simultaneously beamed into space from the Cerberus Deep Space Ground Station on June 15, 2018. The target was a binary system nearly 5,000 light-years away, known as V616 Monocerotis. It's composed of a star about 1/3 the mass of the Sun and a black hole. At the time, it was the nearest black hole to the solar system, although it has since been dethroned by at least a few other candidates. Now, paying tribute to Stephen Hawking by beaming his voice into space may seem like an odd choice, considering he was a very outspoken critic of METI. But as explained by his daughter Lucy, the broadcast was a purely symbolic gesture intended not only to celebrate his scientific contributions, but also to fulfill his lifelong dream of going into space. This is further reflected by the transmission target, as Hawking dedicated much of his life to the study of black holes. Besides, we're hardly going to make contact with aliens in the vicinity of a black hole, right? Well, so about that. This is a view of the solar system, showing all 5 interstellar spacecraft that humanity has launched to date. If we zoom out a bit further, we can see 23 of the nearest star systems targeted by at least one of the radio transmissions mentioned in this video. But to see the 2 most distant targets, we have to zoom out to a galactic scale. Here we find V616 Monocerotis, the target of Stephen Hawking's memorial broadcast, and finally Messier 13, the target of the Arecibo message. But this is by no means an exhaustive list. Some radio transmissions, marked here in gray, did not make the cut because they failed to meet one of two criteria that I made up for this video. The first one is that a transmission must be deliberately directed at an extrasolar target. After all, the goal of METI is to contact another intelligence, so projects that aimlessly blast messages into space with no particular target in mind do not count. This includes signals that could accidentally be detected, like those routinely transmitted by astronomers to communicate with spacecraft or map the surface of bodies within the solar system. To give you an example, in late 1962, a group of Soviet astronomers used this absolute beast of a telescope to bounce radar signals off the surface of Venus. For a bit of fun, they decided to modulate the radar pulses to spell out the words Mir, Lenin, and USSR using Morse code. This is sometimes described as the first interstellar message because a lot of that radiation went right past Venus and continued on into deep space. Now, if you read about this online, you'll find claims that some portion of that excess radiation is currently heading for an obscure binary system known as HD 131336 that's well over 1,000 light years away. The phrasing can often make it seem as though this was planned by the original scientists back in 1962, but that is not the case. The true source of this claim is a forum post from 2002 in which an amateur astronomer did some quick back-of-the-napkin calculations to suggest HD 131336 might have been near the path of the signal depending on the precise time of transmission, which is unknown. Given the imprecision of that guesstimate and the fact that the intended target was Venus, I decided not to include it on my list. The second criterion is that the strength of a transmitted signal must be greater than 100 megawatts. Now, for any radio astronomers watching, here I'm not talking about output power, but the much more crucial parameter, which is the effective radiated power that accounts for things like transmission frequency and gain of the antenna. For anyone curious, you can find a spreadsheet in the references with all the incredibly exciting technical details. Anyway, there's nothing special about the 100 megawatts. I just needed some way to filter out some of the weaker transmissions from the stronger ones, and this seemed like a nice, even number to draw that line. It's neither so high that everything is excluded, nor so low that everything is included. It's just a way to rein in the scope of this video. While I tried to be as forgiving as possible with these two criteria, you could of course be a lot more strict. For instance, it is very common to categorize METI experiments based on how earnest or frivolous most experts perceive them to be. Take the Doritos broadcast project as an example. It is typically not regarded as a genuine attempt at METI because transmitting a commercial into space is obviously just a publicity stunt. It's rather silly, unscientific, and utterly indecipherable. To use the terminology favored by Alexander Zaitsev, it's pseudo-METI. But as I've stressed multiple times throughout this video, what we say isn't all that important because we're probably not going to be understood anyway. What is important is that the signal has been modulated or manipulated in such a way that it does not resemble anything else in the universe. As long as the recipients are unable to ascribe the signal to a natural source, they will have no choice but to entertain the possibility of intelligent design. Besides, the distinction between genuine and pseudo-METI is highly subjective and inconsistent. For instance, the Arecibo message is usually upheld as a prime example of METI, despite Frank Drake himself describing it as a publicity stunt, and much of it is indecipherable. Likewise, the message to Altair is typically regarded as genuine METI, even though the Doritos broadcast project was about 5 times more powerful and lasted 6 times longer. Another approach would be to sort METI experiments based on the distance to and habitability of the target. You could, for instance, exclude the Arecibo message because M13 is extremely far away and unlikely to be habitable. Same thing with Stephen Hawking's memorial broadcast directed at a black hole many thousands of light years away. But here's where things get a bit tricky because how do we determine when a target is too far away? In other words, how do we know when a signal is too weak or sufficiently strong to be detected by an alien civilization of which we know nothing about? The simplest approach would be to assume the recipients are no more advanced than us and use our present level of technology and scientific understanding as a baseline for detectability. In other words, if we can't detect it, neither can they. If that's the case, they would definitely struggle, if not be outright unable to detect some of the messages mentioned in this video. But should we really make that assumption? Well, to paraphrase Carl Sagan, any civilization even just slightly behind us wouldn't be able to receive or transmit, whereas any civilization on par with or billions of years ahead of us could be. Odds are they will be more advanced, making range and detectability estimates based on the assumption that they're not feel rather pointless. But it feels equally pointless to assume that they are more advanced, because then it just comes down to who writes the best science fiction. Does more advanced mean they have instruments that are similar to our own but simply larger and more sensitive? Does it mean they have long since abandoned radio technology in favor of something else entirely? Does it mean they have a more sophisticated understanding of physics and that their technology will appear to us as nothing short of magic?
I think it is a kind of intellectual chauvinism to assume that all the laws of physics have been discovered by the year of our meeting. Had we held this meeting 20 or 40 or 80 years ago, we would perhaps have erroneously drawn the same conclusion. We can only do our best with what we have, at whatever point in our technological evolution we are. But there will always be the possibility of yet undiscovered laws of physics. I think it would be a mistake not to bear this possibility in mind.
Habitability estimates suffer from a similar problem because we obviously don't know if what we regard as habitable is the same as what they regard as habitable. Even if we assume that intelligent life can exclusively emerge on Earth-like planets orbiting Sun-like stars, that does not mean they will stay there. Perhaps there comes a time in the lifespan of any civilization when their energy requirements outpace that which can be provided by sun-like stars. Perhaps life is destined to seek out more extreme environments that we would never even think of as being habitable today. Perhaps the messages we've sent towards places most unlike our own are the most likely to receive a response. All this ambiguity is of course a big reason why many are so opposed to METI, because the unknown allows us to imagine the worst. For instance, in early 2010, Stephen Hawking cautioned against deliberate communication attempts out of concern that aliens might not be too dissimilar from our past and present selves.
We only have to look at ourselves to see how intelligent life might develop into something we wouldn't want to meet. If aliens ever visit us, I think the outcome would be much as when Christopher Columbus first landed in America, which didn't turn out very well for the Native Americans.
As we've already seen throughout this video, this pessimistic view on humanity and first contact is very common, and for good reason. There are plenty of examples throughout human history in which a less developed society suffered at the hands of a more advanced one. The problem with pessimism, though, is that it's one-sided. It would be just as easy to leverage more positive trends and behaviors in support of an optimistic outcome. For instance, consider this critique by philosopher Guy Kahane.
Are we to suppose that an intelligent life form vastly superior to us in scientific understanding and technological capacity would still follow simple goals not much different from those of the conquistadors? To answer yes is to take a deeply pessimistic view, not only of possible alien life, but also of human morality. It is to predict that humans would not be significantly better in 100 or even 500 years, even if scientific and technological progress continues unabated.
Considering how much we've improved in a very short span of time, things like child mortality, homicides, and poverty are declining, while access to clean water, electricity, and life expectancy are increasing, we only have to look at ourselves to see how intelligent life might develop into something we would want to meet. Perhaps not humanity of today, since, there's still plenty of room for improvement, but if we project these positive trend lines sufficiently far into the future, it's possible that much older civilizations will have long since outgrown their more destructive tendencies.
I don't believe aliens will pose a threat. I think that hostile tribes bent on war, be they terrestrial or extraterrestrial, destroy themselves with their own weapons long before they have any notion of how to attempt interstellar travel. Now, the more peaceful nations who study science and have perhaps cracked the secret to immortality are more likely to be benevolent, shy, and wary of contact for their own good reasons.
Just as Hawking justified his belief that aliens will be hostile by saying, "Look at all the bad things we've done," Frank Drake justified his belief that aliens will be friendly by saying, "Look at our capacity for growth." Neither argument is more or less valid than the other because we're obviously capable of both. But as the anti-METI crowd will often point out, this uncertainty is the problem. They will often argue that the mere possibility of an existential threat outweighs any potential benefits. To reiterate a quote from much earlier in the video,
"You see, it's not that I'm paranoid. I feel that there will be many civilizations that want to be our friends. However, it only takes one with a contrary point of view to ruin our day, our existence. Before people start sending signals into space on my behalf, I'd like them to ask for my permission."
A common counter-argument among those in favor of METI is that it's too late to worry about hostile aliens because we've been leaking radio signals into space for the better part of a century. Anyone within about 100 light-years of Earth could, in theory, detect our presence by intercepting our television broadcasts. But as opponents of METI are often quick to point out, this unintentional leakage is extremely faint and diffused. While it's impossible to say what signals are too faint for an alien civilization to detect, a weaker signal is obviously more difficult to detect than a stronger one. But it's not just about signal strength, it's also about intent. An archer blindly shooting arrows in random directions is a lot less likely to strike a bullseye than the archer aiming for the target. Sure, radio leakage could accidentally expose our presence, but METI goes out of its way to maximize that outcome. It's the difference between a ship lost at sea that happens to spot the faint glow of a coastal town and a lighthouse. There isn't much we can do about the former because it's merely a byproduct of our civilization, but there's plenty we could do about the latter, like, not build a lighthouse. While some critics advocate for precisely that, a planet-wide ban on METI, such proposals are often countered by what's known as the SETI paradox. It goes something like this: if we conclude that METI is too risky, and other civilizations reach that same conclusion, what would be the point of SETI if no one is transmitting? To quote the man who coined the term, the SETI paradox leads us to an inevitable conclusion. Either we do both METI and SETI, or we do nothing. The obvious problem with this argument is the assumption that all civilizations independently and inevitably reach the same conclusion. Even if we decided to cease transmitting tomorrow, that does not mean all other civilizations must behave as we do. In fact, this argument doesn't work even if METI is universally rejected, because an absence of deliberate emissions does not preclude the detection of unintentional ones, even if it is a lot less likely. So the SETI paradox isn't much of a paradox at all. It makes perfect sense to keep listening, even if we never send another message. But this is just a hypothetical, of course, because we probably will send more messages in the future. After all, a planet-wide ban would be extremely difficult to enforce, which is why some critics seek not to keep quiet, but to regulate the noise. While there's no consensus on what form such regulation should take, popular ideas include an international treaty or policy that places restrictions on METI, some sort of review board or oversight committee elected to make decisions on humanity's behalf, or a democratic process where, presumably, everyone in the world gets a vote, and the logistics of which I don't even dare to think about. While different policies and regulations could go a long way to reduce the number of transmissions, they're unlikely to eliminate the practice entirely. If people want to do something badly enough, there will always be a way to do it. Outlaw METI in one country and people will go to another. Make it illegal around the world and people will do it in secret. Hell, I wouldn't be surprised if a few messages have been dispatched in secret already. Think about it. Radio telescopes have been around for well over half a century. You're telling me not a single person has had the means and motive to beam a quick text to Proxima Centauri when no one else was looking. I'm not saying it's common, of course, but not once?
Proxima Centauri, that's what I'm saying.
The first members of our species to leave Africa about 100,000 years ago.
That's what we need to be sending to if we're going to do it.
To deter their travels.
I told you yesterday.
European explorers of the 15th century sealed
Proxima Centauri is the nearest star to us, and it's got a habitable planet going around it. That is where we should be sending signals if we're going to do it. Like I said, I'm dubious about doing it anyway. But if you're going to do it properly. That's where we should be sending it. Like he said, you're telling me no one's sent a message to Proxima Centauri? Probably have.
Off into the unknown, with death or discovery being about equally likely. Many died, but some discovered new continents. We are a
Anyway, this is almost over. I'm going to put on a thing about 3i Atlas.
Science is a curiosity-driven venture. We will never stop being curious and seeking new knowledge, unless or until it kills us.
As pointed out by evolutionary biologist Wallace Arthur, we are, for better or worse, a species that cannot stand not knowing. Whether it's the other side of a mountain, the other side of an ocean, or the other side of the galaxy, the unknown will always evoke fear in some and irresistible curiosity in others. No amount of debating is going to change that. Now, fortunately for those of you in Camp Fear, METI is extraordinarily unlikely to succeed. The stars we've targeted so far only account for a tiny fraction of the hundreds of billions of stars in the galaxy, most of which are within just a few tens of light years.
And that's
of Earth,
exactly why I'm
even though
saying why they've chosen these crap ones.
the galaxy is about 100,000 light years across.
Yeah, so
For
why
one
are
of
we
our
targeting?
messages to
Why
be
haven't we got
received,
better
the Milky Way is
targets?
either so jam-packed with communicative civilizations that it's basically impossible to miss, or we would need to be luckier than the combined luck of all humans who have ever lucked, and then some. It's still fun to think about, of course. In the same way it's fun
that
to
was
think
good,
about other
wasn't it?
probabilities.
That's
like
taken
winning
him
the lottery.
a year to make, I think.
It could happen, but it's probably not going to. So, in my view, it doesn't really matter either way, but if I had to pick a side, I think I'm more persuaded by the arguments against METI than those in favor. As much as I would like to have confirmation that we're not alone,
It's a waste of
tying
time.
one end of a
Yeah.
rope around your
It's a
waist
waste of
and
money.
the other end around
Yeah, it
humanity
is.
before
Even though
sprinting
it's-
headfirst into a dark
Yeah.
room, hoping there isn't a hole in the floor, is probably not the wisest approach.
Yeah.
Thank you for watching.
Yeah, I agree. It's interesting, but it is a waste of time and money, really. I mean, unless you're going to beaming something to Proxima Centauri, or like something that's a really good candidate and pretty close, where you're going to receive a message back in the next decade or something. You know, you're not waiting 7,000 years for a response. If you could get a response in a few years, and it's got a really high chance of it's a habitable planet, then if you're going to do it, that's where you should do it. But then again, should you be doing it? Should we be doing that? Probably not. Even though it's exciting to do and fascinating, and it's like human endeavour, and we're curious and we want to know, are we alone and all that. I get that, but should we be doing it really? It sounds like we're just staying in our box, doesn't it? But we probably shouldn't be doing it. We probably shouldn't be. But anyway, it is a waste of time and money, really. But then again, it is interesting. Anyway, let's get this on. Because this is interesting as well. Right, I'm going to shut up.
There is a very strange object flying past our sun. We don't exactly know what this thing is or what it's doing. We can't even see it anymore. But we have been watching this object very closely for months. We've given it a name, 3I Atlas, and we've given it a title, Interstellar Comet. There is a lot that we know about this new visitor to our solar system. In just 4 months, there have been nearly 100 research papers published on 3I Atlas, and there is plenty of other information out there that doesn't appear on the official record. Some of it can sound pretty insane. So today, we're going to cut through the noise, and we are getting to the bottom of everything you actually need to know about 3I Atlas. Let's talk about the journey of this interstellar object. Right now, 3I Atlas is making its closest approach to the Sun. We call this phase perihelion, and the peak occurs on October 29th, when the object will pass within about 210 million kilometers of our star. Although in space we typically use a larger form of measurement, that's the astronomical unit, or AU. 1 AU represents the average distance between the Earth and the Sun, which helps us to bring a familiar sense of scale to the vastness of the solar system. So the perihelion of 3I Atlas occurs at 1.4 astronomical units away from the Sun, which means it doesn't actually get that close. It's somewhere just inside the orbit of Mars. But this will be the time of peak activity for 3I Atlas. This is the hottest that it will get, which means that a lot of material from the surface of the object is going to get blasted out into space. Now, that's normal for a comet. We call this process sublimation. It's what happens when a solid material transitions directly into a gas, because there's no liquid in the vacuum of space. And sublimation is what gives a comet its distinct look, with a fuzzy halo and a long tail. The halo is made of all the gas and dust being ejected from the hard surface of the object. It's technically known as the coma. The tail is created by solar wind. That's a name for the waves of radiation that constantly flow from the surface of the sun. This wind blows back all of the lightest bits of dust and gas from the coma and pushes it away from the comet. It's a spectacular piece of cosmic ballet, and unfortunately, we don't get to see this happening to 3I Atlas as it flies through its peak exposure to the sun because we are on the wrong side. Call it fate or call it something else, our view of the perihelion is completely blocked out by the glare of the sun. Okay, so we know where 3I Atlas is right now, and we have a pretty good idea of what it's doing, so while we wait for it to reappear on the other side, that gives us an opportunity to investigate how it got here in the first place, and this is a deeply fascinating story. We have been tracking 3I Atlas since July 2025. It was officially spotted by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, which is actually a bunch of telescopes all around the world in places like Hawaii, Chile, and South Africa. What they do is stare at the night sky and look for moving objects. And that is what they saw on the night of July 1st, just another moving object. So they classify it as a new asteroid and they're ready to move on. But then they notice something weird about this one. It's moving too fast. Everything in space is constantly in motion, and every object in the solar system rotates around the sun because we are all trapped by its force of gravity. The fact that we are moving is what keeps us from falling into the well of gravity, and the closer you get to the sun, the faster you have to move in order to stay afloat. But if you start to move fast enough, then you actually start to rise up out of the well. And if you reach a certain velocity, then you break free completely of the sun's gravity and you can fly out into interstellar space. You enter the void of nothingness that exists between stars. And when astronomers clocked the velocity of this new asteroid, they were shocked. This was the fastest moving object ever detected in our solar system. Let's establish some scale here. The planet Earth orbits the sun at a speed of 30 kilometers per second. That's us. We're moving pretty fast and we're pretty close to the sun. But there are planets that are a lot closer. Here is Mercury, 0.4 astronomical units from the surface of the sun. It gets cooked, and to avoid falling into the gravity well, Mercury has to orbit at a velocity of around 48 kilometers per second. The new object discovered by Atlas was moving at 58 kilometers per second, and at the time, it was still way out there, just inside the orbit of Jupiter. That's about 4.5 AU away from the sun. And at that speed, it was clear that this object was going to blow straight past the sun and just keep on going. We call this a hyperbolic trajectory, meaning that this thing had come from the void, from interstellar space, and that's where it was going to return after completing its grand tour of our solar system. This is when the name 3I Atlas came to be, Third Interstellar Object, which means there were two before it. You probably know this one, Oumuamua, the first ever identified interstellar visitor, and it was also pretty weird, although it was weird in a totally different way than Atlas is, and we'll get deeper into that very soon. But we also have a second interstellar object, the often overlooked middle child, 2I Borisov, which was actually not that weird. Aside from the fact that it was interstellar, it basically just acted like a normal comet. So, if anything, it was weirdly not weird. There are three big differences between 3I Atlas and its interstellar siblings. One is size. It's literally much bigger. Oumuamua was up to 400 meters across. Borisov was as wide as 1 kilometer, but 3I Atlas could be up to 5.6 kilometers in width. 2 is speed. Atlas travels at about double the velocity of Oumuamua and Borisov. And 3 is the direction that the object came from, and this is the really weird one. Oumuamua came in from above, from the northern sky, which is the general direction that the solar system is moving. So We're all orbiting the sun, but the sun itself is also orbiting around the center of the Milky Way galaxy, and it's dragging us along with it. So as much as Oumuamua hit us, we also kind of ran into it. 2I Borisov did mostly the same thing. It came in at more of a diagonal angle than straight on, but from the same general direction. Now, 3I Atlas is not another head-on collision. This one is a T-bone, and it's coming in on that side angle in almost perfect alignment with all of the planets. Our solar system is like a disk of stuff that all formed around the sun. Over time, all of that stuff kept smashing into each other and forming into planets and moons and asteroids and things, but it all remained in a relatively flat disk shape. We call that disk the plane of the ecliptic. There are only a few things that are a little bit offset from that plane. The most recognizable one would be Pluto. Its orbit is tilted by 17 degrees, so sometimes it's a little above the plane of the ecliptic and sometimes it's below. It's important to know that so we can appreciate how well aligned 3I Atlas actually is. The interstellar object is only 3 degrees off from that ecliptic plane. It hit our solar system in perfect alignment with the disk. Space is three-dimensional, and that object could have come from any direction. So to have something hit us almost perfectly side-on, it's a very big coincidence. But that leads us into an even bigger question. Where did 3I Atlas come from? Well, we know that it came from the direction of the galactic core. So if we look at the Milky Way galaxy from this usual top-down perspective, you are here in this kind of outer half of the galaxy, located in a spiral arm. When you see the Milky Way in the night sky, that's the next spiral arm over. Anyway, 3I Atlas came from the direction of this bright core in the middle. It's bright because it's full of stars, and they're packed together much more tightly than the ones in our neighborhood. But again, space is three-dimensional, so to really understand where 3I Atlas originated, we need to flip the galaxy over to a side view. And just like our solar system, most of the stuff in the Milky Way is concentrated in a thin disk around the core. But also like our solar system, there are a few things that kind of hang out above and below the thin disk. In the galaxy, we call that area the thick disk. It's a lot less crowded in the thick disk, so you don't get nearly as many giant collisions and supernova explosions and black holes and stuff. So things in this region tend to just hang out undisturbed for very long periods of time. And that's where astronomers believe 3I Atlas came from, this ancient region of space, which could make it as old as 7.6 billion years, nearly twice the age of our own planet. Now, we'll probably never be able to trace the journey of 3I Atlas all the way back to its point of origin, but astronomers have recently managed to backtrack over 10 million years, and they've identified 93 stars that the object would have encountered over that period. But what's deeply fascinating is that over the course of that 10 million years, the closest it would have come to any of those 93 other stars was a distance of 0.3 light years. That's 63,000 astronomical units. And right now, 3I Atlas is just 1.4 AU away from our own sun. Now let's talk a little bit more about how 3I Atlas approached the sun and what we learned about it along the way. Even though 3I Atlas was officially discovered on July 1st, it was actually spotted for the first time on May 7th, 2025. It showed up in images captured by the Transiting Exoplanet Survey Satellite, or TESS. It's an observatory that orbits the Earth and looks deep into the galaxy, trying to identify new planets in other star systems. And for a period of about 1 month, TESS just happened to be looking in the direction of 3I Atlas. This gave us the opportunity to track the object as it moved through the orbit of Jupiter. The first thing that astronomers wanted to measure was the object's brightness and how it changed over time. That's going to tell us about what this thing is made of. We know that in the 1 month period that 3I Atlas was observed by TESS, it traveled about 1 AU in the direction of the sun, so we would expect it to get brighter over that time. Astronomers use a term called flux to describe the perceived brightness of an object in space. Here's an example of how this works. Think about how bright the sun appears from your location at noon on a clear day. Now imagine you're transported to the surface of Mercury. That same sun is going to suddenly appear a whole lot brighter, bright enough to incinerate you. Now, the actual brightness of the sun didn't change, only your perception of it. That is flux. So astronomers had a hypothesis that the flux of 3i Atlas would increase by a factor of 1.5 between May and June. But data from tests showed that the flux actually increased by a factor of 5. So there was a massive increase in the amount of light being reflected by this object. And that's how we know that this isn't an asteroid. So it must be a comet that's beginning to form its coma of gas and dust, which is what's reflecting all of that excess light. Only there are two weird things about this observation. One has to do with the polarization of light. Now, this is a tough one to explain, so we're going to oversimplify here. When light from the sun hits that cloud of gas and dust around 3i Atlas, it's going to scatter in different directions. But the direction that the light bounces is not random. It can tell us a lot about the material that the light is hitting. If the light scatters off to the side at a right angle or perpendicular, then we call that positive polarization. If the light bounces straight back in a parallel direction, then we call that negative polarization. Most objects in space have a mostly positive polarization, even interstellar objects. 2i Borisov was positive, but 3i Atlas is negative, and not only that, it has the most extreme negative polarization of any object ever discovered. That is pretty weird, and it's just one of the many oddities about 3i Atlas that tells us not all solar systems are the same. What we think is normal here would be weird somewhere else, and what's normal in a different star system is considered weird around here. And then the second surprising thing about the coma of 3i Atlas was the fact that it even existed at all. Remember, we're looking at this period between May and June, and 3i Atlas is still way out there beyond the orbit of Jupiter. This is over 5 AU away from the sun. It's cold out there. It's so cold that we don't typically spot comets at 5 AU because they typically have not begun to form their coma yet. They're still frozen solid. It's not usually until somewhere between 3 and 4 AU that the sublimation process really kicks in. And that's because typical comets from our solar system are typically made of water ice, which needs a lot of energy to melt. But as we continued to observe 3i Atlas and we started pointing our most powerful telescopes directly at it, we learned that the coma was actually dominated by CO2 gas. It did have some water vapor, but the ratio of CO2 was much higher at around 8:1. That's basically the opposite or inverse of what we are used to finding in comets. If you've ever seen dry ice before, it's typically used to create a smoky effect for live performances. That's frozen CO2. It has to be created and stored at incredibly cold temperatures. And as soon as it's removed from the deep freeze, dry ice will instantly begin to sublimate, making that signature cloud of gas. That is what 3i Atlas was doing way out there in space. And that's why its coma formed so early, because CO2 ice melts at a much lower temperature than water ice. And we've continued to observe 3i Atlas on its approach to the sun. We've seen that ratio of CO2 and water begin to flip. By late in September, as it was passing through the orbit of Mars at just over 1.5 AU, the object had actually begun to release a massive amount of water vapor, about the equivalent of a fire hose running at full blast, which is actually more water than we would expect even from a normal comet at this distance. We've never seen so much water vapor appear so suddenly. The same thing can be said for metal in the coma of 3i Atlas. When it was observed over the summer, astronomers detected a small amount of nickel in the surrounding cloud, but they did not detect any iron. So a couple of things to note here. One is that nickel and iron are pretty common in the universe because they are formed inside the core of a dying star. Then that star goes supernova and blasts these metals out into the surrounding area of space, where it gets pulled in by new stars that are beginning to form their own planetary disk, and then the process repeats. So because nickel and iron come from the same place, they're typically found together in planets, moons, asteroids, and comets. So when we see a lot of nickel but no iron, we wonder where the iron went, what process separated them. And thing number two, it's weird to see any metal at all sublimating from 3i Atlas given its distance to the sun when this observation was made. It's still way out beyond Mars in the region of the asteroid belt, which is still very cold, and the process of sublimation is driven by heat. Now, when it comes to CO2, we know that it doesn't need much heat in order to melt, but when we're talking about metal, there's something else going on. Likely, the massive release of CO2 is dragging nickel atoms along with it, but that still doesn't account for the iron deficiency. Now, just like water vapor made a very sudden appearance in the coma of 3I Atlas, the same thing did eventually happen with iron. By late into September, astronomers had started to detect iron for the first time in the coma, and then, very quickly, the ratio of nickel to iron changed to a more normal combination of the two. So 3I Atlas is becoming more normal over time, but it's getting there in a very strange way. Now, let's talk about tails. This is another area where 3I Atlas has behaved a little different from your average comet, and that's mostly because the first time we saw a tail forming around 3I Atlas back in the summer, it was pointing in the wrong direction. This object initially formed a sun-facing tail. This is unusual because the tail is considered to be an effect of the solar wind interacting with the coma. The solar wind blows away from the sun, so therefore we expect the tail to flow in that direction. In this case, it didn't, which could be related to the early formation of the coma, which was due to the high CO2 concentration. Because the object began sublimating at a very long distance from the sun, it's possible that the solar wind just wasn't strong enough yet to push the cloud of gas and dust away. So what we saw was more of that cloud accumulating on the warm side of the object, the sun-facing side, before it encountered a strong enough wind to form a conventional tail, which is what 3I Atlas eventually did. By September, a short fan-shaped tail facing away from the sun had developed, which is pretty normal. Not all comets have long streaking tails like what we're used to seeing in illustrations. The length of the tail varies according to what the comet is made of and its distance to the sun. For example, Hale-Bopp is pretty famous for having a gigantic tail when it was observed in 1997, but it was also very close to the sun at that time, about 0.9 AU, 1/2 of an AU closer than 3I Atlas will ever get to the sun. So, of course, it experienced more sublimation and solar wind, which shaped that tail. And it's around this time that we actually get our closest possible observation of 3I Atlas, but the view doesn't come from the Earth, it comes from Mars. On October 3rd, the object passes within 0.19 AU of the planet Mars, the closest it will come to any planet in the solar system. And this is lucky for us because we have a lot of cameras on and around the red planet, which means we were able to use them to image 3I Atlas. Here is a photograph taken by the Perseverance rover from the surface of Mars. This is how the object would have appeared in the night sky. It's not a great picture, this isn't what the rover's camera was designed for, and in order to see this much light, the camera had to take 30-second long exposures, then several of those images were stacked on top of each other, so what you end up with is more like a streak than a defined object. And here is another image of 3I Atlas taken by the European Space Agency's ExoMars probe, which hangs out in orbit around Mars. We can see the object a little more clearly now, but there's still not enough resolution to distinguish between the bright coma and the surface of the object itself. In order to get that fine detail, we would need to take a photo with NASA's Mars Reconnaissance Orbiter, which has the most powerful telescope in the Mars system. Unfortunately, at the time we are making this video, that image has not been released, if it was even taken at all. Basically, there's been a shutdown of the US government, and people at NASA aren't going to work until some political stuff gets resolved, which unfortunately could take some time. But time is something that we have right now, because the sun is going to continue blocking our view of 3I Atlas until early December, at which point we'll be able to study the effect that the sun had on the object, although the closest that we'll get is still 1 AU. That happens on December 19th. At this point, 3I Atlas will be well on its way out of the solar system, but there is just one more close encounter still to come. On March 16th, 2026, the object will fly within 0.36 AU of Jupiter. While we don't have nearly as many cameras around Jupiter as we do at Mars, we do have one. It's on a probe called Juno, which has spent the past decade observing the gas giant and its moons. but it will have a chance to take one last image of 3i Atlas before it disappears. Now, at this distance, the object will be cooling down. It's going to be less active, but it could be changed by its exposure to the sun, and that will add an extra layer of understanding to these interstellar objects. It's entirely possible that a lot of these strange characteristics didn't even come from the place where the object was formed. It's just an accumulation of weird stuff that it picked up along the way. For now, we can only wonder, but more answers, and probably more questions, are soon to come.
Okay, interesting stuff. Right, this is looking mountainous. Right, I'm gonna keep the camera, keep the microphone on now. Right, yeah, it's looking like we're gonna have to be dodging round some mountains coming in. So I hope we can see them. I hope the cloud is looking a bit cloudy, but yeah, and also it's saying we're at 9,700 feet. I very much doubt that. I feel like we're more like at 5,000 feet rather than 9. So yeah, the altitude is not going to be accurate on this screen at all. And yeah, we're going to have to be swerving around some mountains. Also, the flight's seeming to be longer than... I feel like it's about 1 hour and 10 now, and we're still 10 minutes away. So yeah, the flight's going to be a quarter of an hour longer than projected, I feel like. But anyway, yeah, we're getting pretty low here. This feels like 2,000-3,000 feet up. So yeah, the altitude is a lot higher here than it was in where did we come from? For Gaborone, Botswana was a lot lower altitude than Windhoek, Namibia. So yeah, bearing that in mind, yeah, it's saying we're at 7,000 feet now, more like 2. Yeah, there you go. There you go. See? I'm pretty good, I know. Yeah. So the actual altitude is 2,000. So yeah, we're 5,000 feet higher up altitude-wise here in Windhoek, and we're going to have to swerve around some mountains. But it's not a problem. I'd rather be too low than too high up and having to nosedive it in and worry about a lot of things. As long as we don't hit anything, obviously. But yeah, so yeah, we are at 2,000 feet. And coming in hot. Yeah, I can see a mountain directly ahead of us. I think the runway's on the other side of that mountain there that we can see through the mist. It's like something out of Lord of the Rings. Rightio. Right, I'm just going to play this by ear and see what we have to do. I'm going to zoom in on here. But it is an interesting scenario that we've got. Yeah, I feel like what I'm going to do is go round this mountain here. You can sort of see it on the VFR map. The darker the brown, the higher the altitude. So no green round here, because green is like sea level, and then obviously you get darker greens, and then you're into like yellows and browns. You can see like there, up here in the top left is a slightly lower altitude. There's even a bit of a lake up there. It's a slightly paler green. We're getting into browns. And then here is like almost a dark brown, i.e. a mountain. So, and the runway, I think, is running like this, south to north to south, like this. So what I'm probably going to do is get to about here and then come round the mountain, reduce the speed around here, and then come in like that. That is my initial sort of... But interesting. Listen, you don't want every flight the same, do you? So an interesting challenge at 1,400 feet off the ground. So yeah, we are a little bit lower than I'd like to be. I'd like to be at 3,000 or 4,000 feet right now. But yeah, we'll do the big swerve around this mountain here, or mountain range, if you like. I'll zoom in. Maybe like that might be ideal for us. Something like that. And yeah, we'll pull a left-hand turn pretty quickly and then get the speed down. But yeah, interesting. interesting descent. Right, let's have a gander. Right, I'm going to take manual control in a minute, and we're going to head south, or southwest if you like. Yeah, we're going to head southwest and then north into FY. Let me write that down. Actually, we're not going to hit anything out. FYWE. Well, it's interesting this. Yeah, right. I'm gonna turn now. I don't want to leave it too late. I don't want to be scraping the wing on the side of a mountain, do I? And so we'll take off autopilot now, and we shall give it the old swerve. But yeah, we're very low, aren't we? We're 1,300 feet off the ground, and yeah, there's a runway in sight. Really? Well, what's going on here visually? What is going on here visually? Wow, is this mountain not rendering in properly, or what's the game here? Right, I'm happy with that trajectory. Okay. I'll reduce the speed soon. Chilling at 1,100 feet, of course we are. I mean, I am tempted to pull up. I mean, let's see if we get a gap through this mountain here. Let's see if we get a gap. If not, I can come up. You know, autopilot's off now, and yeah, cruising around in the mist. It's not ideal, really. Cleared visual runway, yeah, on the other side of the mountain. I don't think we've got a visual, mate. It might come up a little bit actually, because it is looking a bit dangerously low. So I'll just come up a little bit. But yeah, well, certainly different, isn't it? Get that as a screenshot. Namibia, bringing obstacles to the game. Wow. Oh, and a hell of a lot of cloud cover just where we don't need it as well. Yeah, hence why I'm coming up. Looks like I say, yes, it looks like a volcanic eruption. I hope there's not a mountain hiding behind that cloud. Well, actually there is. Actually, what I might do is start to come round this way now. Right, this is wow, this is a challenge. Right, I'm going to start reducing the speed as well. Wow, this is a challenge. This is certainly something different. Windhoek, Namibia, throwing obstacles at me. Right, well, you don't want to, like I say, you don't want them all the same, do you? Oh God, if we hit them out. No, it's all good. It's all good. It's all good. I think. Ooh, can I see? No, I think we're all right. I think we're all right. Looking at the map, I'm going to start turning us in. We'll go flaps 1. Wow, into the rain we go, into the cloud, with unknown terrain below us. Well, I can just about see the outline of some mountains there. Yeah, I tell you what, we'll come down. Oh, I'm not liking this visibility. Right, okay. Wow, this is a challenge. Right, let's have a look. Let's zoom in a little bit more. Okay. Okay, we are pretty close as well. Right, wow, this is interesting. We'll go flaps 2 then. So we're slowing it right down now. Sensible thing to do. Hopefully get some more visibility as we clear these mountain tops. Yeah, actually, I'm quite liking it. I mean, wow. I mean, well, Namibia coming up with the scenery. Fair play. It's been flat land. It's been pretty flat. Whoa, steady. Don't hit that. In fact, we want to be coming over this way anyway. But wow, yeah. I mean, Africa's been pretty flat, hasn't it? Until Namibia, where it's wow. Well, there you go. Geography lesson. There you go. Yeah, we're going to coming over this way anyway. We'll get the wheels out now, and we're coming down on speed nicely. And yeah, wow. Hopefully it starts leveling out now. I think it is. I think we're over the most extreme sort of. Well, there you go. What a shot that is. Right, brilliant. Okay. So we'll just head over this way and hopefully see a runway pretty soon. Right. Okay. I'll need to be seeing a runway right about now. Let's. Oh. Now. Oh yeah. No. Yeah. Yeah. We need to come way over here. We'll go full flaps. Yeah. We need to come way over here. Wow. This is. Wow. Okay. This is going to be a late swerve. Let's make sure we're low enough. Yeah, this is going to be wow. Wow. Oh dear. Okay. Don't crash it in Namibia. Okay. Okay. Oh wow. What is going on? Where is it? Where's the end of the runway? We're pretty much on top of it. Okay, this is a very unusual angle. And golf course. Rightio. Oh dear. Oh dear. Oh dear. Right, this is extremely narrow, isn't it? Wow. Rightio, go around it is. Oh, Jesus. Right. Whew. Right, wow. Oh, Jesus Christ. Oh, my God. Rightio. Well, nice one. Nice one, Jones. Okay. Oh, my goodness me. Right, the World Tour was in the balance right there and then. Rightio, let's do it. Let's perform a loop. Oh, my God. Okay, what time are we on? I've got 8 minutes to land this thing. Okay, rightio, we're not going to go any faster than 180 knots. Rightio, shall we perform the big swerve? Let's just bring the power down. Wow, that was, yeah, interesting. That was interesting. Okay, what we want to do is... Okay. Hold on to your hats, ladies and gentlemen. Wow. Keep it full flaps. I know that's probably not the thing to do. We'll get the wheels out again, but yeah, forming the big turn. Back we go. Wow, I think that's the first go around in the World Tour, is it not? I think there should have been other times where should have done a go around and didn't. What we're saying speed wise. Wow, this is rightio. Okay. Rightio. Yeah, we might as well get the wheels out in case I forget later on. So we'll get the wheels back out now. Okay. We're not even on the map. Where are we? Not even on the map, Rev. Come on, where's the fucking plane on the map? Okay. 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 Let's have another go. Well, that would go around. It was certainly a last minute decision, but yeah, no, I was... right, now, where the bloody hell is it now from this side? Right, speed-wise, we are bang on. Right, where the bloody hell is it now? Yeah, forget expedite your bloody climb. Where the bloody hell is it now? These skyscrapers are in danger, aren't they? Right, need to come over here. Right, speed's right, full flaps. Again, it's going to be a late swerve. They're not trying to get it lined up like that. You can see a flashing light there. That's a good sign. Right, come on then. Second attempt. Windhoek, Namibia. From the north. Jesus Christ, those buildings end on the bloody... over the bloody runway. Right, we're getting it down this time. It's narrow as well. Right, we're getting it down this time. We're getting it down this time. Getting it down this time. We're getting it down this time. Getting it down this time. Getting it down this time. Use all your experience, Rob. Use all your... Holy fuck. Holy shit. Holy fucking shit. Namibia. Oh, holy fucking damn it. Oh my fucking god. Oh. Oh my god, Windhoek. Oh my god. Holy shit, bro. Holy shit, bro. Holy. Oh my god. Oh my god. What the fuck? Oh my god, we're down. I don't know how we're down, but we're down. I'm just gonna park it up here, am I not? Oh, Jesus. Why was it so narrow? Why is it so narrow as well? Why is it as narrow as a taxiway as well? I can't believe... Oh my god, that go around as well. I just kicked in the power. It literally... Oh, gee. Oh, watch that back and... That was the worst. That was the riskiest, worst. That was absolutely criminal. How are we still going? I've got to be mad. 99 flights and I'd produce a landing like that after a go around. How is this still going? How is this world tour still going? That was insane. That was insane. Oh my god, this is one of the first ones where I'm looking forward to watching this back myself. Holy shit. Oh my god, my heart was in my mouth when that go around. Oh my god, and even the actual touchdown, we landed at a 45 degree because I was thinking about straightening up at the last minute on that go around. I was thinking about straightening up at the last minute, but it can dip a wing, and I could have dipped a wing into the tarmac, and so I didn't want to do that. So I wasn't being extreme with lining it up at the end. And then so I thought, I'll just no, and then we touched down, then bounced back over, and they were floating at 10 feet above the ground. I'm thinking, Jesus, got it down on the field. Do you know, I wouldn't have been outraged there if it had come up with an error saying I've damaged something. I couldn't have gone, oh, what? No, that was absolutely fine. What are you talking about? I would have had to just accept that I fucked up. But somehow, that must have been right on the limits of the game saying, nah. That must have been on the very limit of the game saying, bro, you've crashed. That must have been on the limit of crash landing. You know, that was the limit of crash landing. That, oh my god, flight 99 is complete. Welcome to Windhoek, Namibia. Local time 3 p.m. Outside air temperature 27 degrees. How have we got this down in one piece? I do not know. First go around as well on the world tour. Yeah, it was lined up that bad. Having swerved around the mountain range a little bit and coming in, I was so far off that there was no last minute swerve that I could have got that down on the first attempt. So I did the right thing and kicked in the throttle. We went round again, and even the second landing was really a go around as well. But I somehow sat it down in the field next to the runway. But damn, that was, oh my god, right, oh my god, we're down. How the fuck, is this plane still in one piece? I do not know. Seatbelts were off as well, so, oh my God, any injury claims, please pass them on to my assistant. Right. Holy, well, it said 1 hour and 15, but that didn't account for a go around. It's got to be 1 hour and a half, hasn't it? Yeah, 1 hour and 24 minutes. Holy shit, that was on the brink. We're down, and that's a big lesson. That's a big lesson. Also, I was under time pressure because I've got to go now, which is not ideal. I want to have, 20 minutes, half an hour in hand in case I have to do a couple of go-arounds. It's not good to be under time pressures. That's a bit of a lesson. And yeah, wow, Namibia throwing up a big obstacle in the Flawless 195 World Tour. But you know the game. We're down, we're alive, the plane's in one piece, and the World Tour somehow, by the skin of its teeth, continues. Oh, Christ, that go around. Oh, no. That was insanity. That was absolutely on the brink. I mean, I know I've said it probably a dozen times. Like, oh, my God, that was so close. But no, this time, I cannot be doing that. That was pushing the limits. That was really, really, really pushing the limits, and we're extremely lucky. If I'm a cat, that was the 9th life. You know what I mean? That was the 9th and final life. So, yeah, I've got to be more risk averse, obviously. But join me next time when we go to South Africa. We're heading to Cape Town. That flight's going to be a little bit longer as well. It might be 1 hour and 3/4. Might be as long as 2 hours directly south to Cape Town. So join me for flight 100 next time out, but that is flight 99, 1 hour and 24 minutes and 32 seconds. Somehow we have got that down on the ground without crash landing, damaging anything, but that was on the brink. Thank you. Join me next time, and whew, I can breathe out. Wow, that was insane. See you next time. And breathe.